first problem of the sheet, 1A, is about two blocks of mass 10 kg and 20 kg placed on the x-axis. One, M1 equal to 10 kgs, M2 equal to 20 kgs, placed on the x-axis. Say at, this is placed at x equal to x1, this is placed at x equal to x2, right? Obviously, they have a center of mass xcm. xcm by definition is m1 x1 plus m2 x2 by m1 plus m2, right? So which is like 20x1, or rather 10x1 plus 20x2 divided by m1 plus m2. Now, what they say is that the first mass is moved on the x-axis by a distance of 2 centimeters. This is moved by a distance of 2 centimeters. It means change in x1 is 2 centimeters. Means delta x1 is 2 centimeters, right? Now, by what amount should the second mass be moved to keep the position of the center of mass intact? That means, let's say x2 is moved by an amount delta x2, and I want to preserve the position of the center of mass. That means delta x of the center of mass should be 0. Change in the x coordinate of the center of mass should be 0. Now, from this, can I not say change in the x coordinate of the center of mass, delta of this is going to be, and this is m1 plus m2, so might as well right away write 30, right, is 10 times delta x1 plus 20 times delta x2 divided by 30. Does it not mean this? Right? And we want this to be 0, and we want this to be 0. We want this to be 0, which means delta x2. That means the numerator should be 0. That means delta x2 should be minus half of delta x1. Delta x2 is minus half delta x1. And delta x1, as you can see, is 2 centimeters. So this is minus 1 centimeter. Now what it means is that if the rightward shift is positive, leftward shift is negative. That means m2 must be moved by minus 1 centimeter to the right. That means 1 centimeter to the left. m2 is moved by 1 centimeter to the left. This is what the minus sign means, right? Clear? And if someone said, well, by what amount should m2 be moved so that the center of mass shifts 2 centimeters to the right, then delta x would have been 2, and you can solve for delta x2, which is what the next problem is all about. So if you allow me, I could skip the next problem, which is in the next problem there is a value of delta xcm non-zero given, and you can find delta x2 from those considerations. So very similar problem, so might as well move to the next problem. Clear? Of mass 10 kg, two balls of equal masses are projected vertically upwards. There are two balls of equal masses, say mm, projected vertically upwards, one from the ground with a speed of 50 meters per second, one from a 40-meter high tower. This is a 40-meter high tower with an initial speed of 30 meters per second. Find the maximum height attained by the center of mass. Now, these are equal masses, right? So, the center of mass of these would be halfway between the two. So if this is 40 meters, the initial height of the center of mass is 20 meters, right? The velocity of the center of mass initially, m1 v1 plus m2 v2 by m1 plus m2, isn't it? m1 v1 m into 30 plus m into 50 by 2m. So that makes it 40 meters per second. m1 v1 plus m2 v2 by m plus m 2m, right? So that makes it 40 meters per second. Yes or no? Do you realize that? M into 30 plus m into 50 by 2m. That is 40 meters per second. Now, subsequent to this, the center of mass is under the influence of gravity. So there is g downwards. And from this point onwards, imagine the center of mass to be a point particle, and it reaches a maximum height from this position. The center of mass reaches a maximum height where the velocity of the center of mass will become 0. This is h max from the initial position, right? The velocity of the center of mass at this position becomes 0, right? The h max then is the initial VCM squared by 2g, which is 1600 by 20, that is 80 meters. Yes or no? So 80 meters from this position, that means 100 meters from the ground, because this is 20 meters. So the maximum height is 100 meters from the ground reached by the center of mass. Yes or no? 80 meters from this original position, it's already 20 meters above the ground, so maximum height from the ground is going to be 100 meters. Yes or no? Right? I'm assuming all of you would have got all of these right without a glitch, right? Number 2, is a pulley arrangement. There is a block A, and at the other end there is a block B. Mass of A is 2 kgs and mass of B is 1 kg. We want to find the acceleration of the center of mass. Okay, first of all, the block A will have an acceleration A downwards, the block B will have an acceleration A upwards. Now, it's easy to compute this acceleration. The acceleration of this is going to be given by MAG minus MBG divided by MA plus MB. Yes or no? Do you realize why so? Right? MAG means 2 minus 1, 1, g divided by 3 is the acceleration of A and B, right? This is downwards, this is upwards. Yes or no? So, and this is a 2 kg block and this is a 1 kg block. So the acceleration of the center of mass, if I take downward positive and upward negative, then the acceleration of the center of mass is going to be m1a1 plus m2a2 by m1 plus m2. Mass of this, so acceleration of the center of mass is going to be 2 into g by 3. I've taken this positive, 2a minus 1 into g. Yes or no? 1 into g by 3 divided by 2 plus 1, m1 plus m2. Right? m1a1 plus m2a2. a2 is minus a. a2 is minus a because it's in the opposite direction. So that makes it g by 9. Down. Positive, therefore downwards. Acceleration of the center of mass is g by 9. Positive and therefore downwards. Yes or no? Again, I expected you would be able to solve this as well, right? Simple, isn't it? Huh? Now there are two identical planks. Problem 3 is about two identical planks. This is one. This is another one. And they are hinged. They are hinged. This is a plank of mass m and length L. And this is a plank of mass m and length L. This is the hinge H. Alright. This is the vertical plank and it starts to fall downwards. We want to be able to find the displacement of the hinge till the vertical plank becomes horizontal. That means it completely rests on the horizontal plank. Right? Now, look, in this system comprising the two planks, this is plank 1 and say this is plank 2. We are assuming that they rest on a smooth surface. We are assuming that they rest on a smooth surface. Now if I look at 1 and 2 together, a system that comprises 1 plus 2, plank 1 plus plank 2. The forces, external forces that are acting on them, Mother Earth, gravity downwards, reaction from the ground. What about the hinge force? Internal, because that's the force they exert on each other. If I look at plank 1 alone, hinge force will be an external force. If I look at plank 2 alone, that's going to be an external force. But if I look at plank 1 plus plank 2, then this would be looked upon as an internal force and would not participate in change of linear momentum of the system per se. System comprising 1 and 2. This is what happens. Yes or no? Huh? Sorry? It's a point particle. It's a point hinge. The length of the plank is the hinge. We will ignore this dimension. This is almost a point dimension. The length is the only consequential dimension here, please. Okay. now, so there are no horizontal forces acting on the system. Do you realize there are no horizontal forces acting on the system? So F in the x direction, which is the horizontal direction, is 0. Yes or no? The initial velocity of the center of mass in the horizontal direction is 0 because the system starts from rest. Both the horizontal and the vertical plank have no horizontal motion to begin with. Right? So the velocity of the center of mass along the x-axis, that means in this direction, is 0. Now the acceleration of the center of mass in the x direction is also 0. Why? Because the net force in the x direction on the system is 0. So the acceleration of the center of mass in the x direction is 0. That means the velocity of the center of mass in the x direction remains 0 always. That means the x coordinate of the center of mass will not change. The x coordinate of the center of mass will not change. See, when this begins to slide, you know, it starts to fall like this. The x coordinate of the center of mass of this will change. Therefore, that means, you know, this rod can be replaced by a point particle here, right? So the center of mass of this is coming leftwards, which means now this must negate that change and must move rightward, so that the net shift in the center of mass of the system comprising this and this remains preserved. X coordinate of the center of mass of the system must be the same, right? Exactly like the plank problem, river raft problem that we looked at in the last video session, right? And you posed so much of resistance. Water did not pose resistance to that raft, but Ayush did. Okay, nevertheless, what you can then imagine is, Imagine that this did not resist and this just fell down, right? If this just fell down, after a while, this plank would simply rest over this without change in position. Yes or no? This mass M would eventually rest like this on this plank. Which means now if that did happen, then originally the center of mass of the system would have been, well, somewhere here. This is the center of mass of this rod, this is the center of mass of this rod. So the center of mass of this rod and this rod in the x direction would have been somewhere, x coordinate of the center of mass would have been somewhere here, yes or no? Not the y coordinate, the x coordinate of the center of mass of the system would have been somewhere here, right? Now, when this falls down like this, okay, then the center of mass of this would have moved L by 2 units to the left, yes or no? The center of mass of this would have moved L by 2 units to the left, and there would have been a disturbance caused. What's the disturbance caused by this small m? M into L by 2? M into L by 2 leftwards is the disturbance caused to the center of mass. Remember the same idea that I pronounced in the last class. The disturbance caused to this is M into L by 2 leftwards. Now, once this has caused that disturbance, M into L by 2 in the summation Mi xi, the total mass 2m will move by an amount x to the right. So the mass 2m will move by an amount x to the right to preserve the x coordinate of the center of mass. This was exactly the point of discussion in the river raft problem. Remember, this is exactly what we did. When this moves down, the disturbance that it has caused in the leftward direction is m into L by 2 to the system. And that must be negated by now the system of mass 2m moving x units to the right, so that the net change in summation Mi xi is 0. Were you there in the last class on the river raft problem? Exactly the same problem, my friend. M into L by 2 is the disturbance caused. Because this is a point particle. The point particle had its x coordinate here, now it has moved x L by 2 units to the left, isn't it? This was here. How much has it moved in the x direction? It has come to this point, right? The center of mass being here of this vertical rod is now here. Imagine this to be a point particle. So this would be like L by 2 units, right? So m into L by 2 is the leftward disturbance, and that must be compensated by 2m, the entire mass moving x units to the right. Not that it happens one after the other, it's the entire process happens simultaneously, but we are simply superimposing for convenience, ease of computation, right? So that means now this entire unit, to compensate for m into L by 2, moves x units to the right, right? X units. So x then becomes L by 4. X then becomes L by 4. That means this entire thing would have moved L by 4 units to the right. That means the hinge would have also shifted L by 4 units rightwards to preserve the x coordinate of the center of mass of the two rods in absence of a horizontal external force. Yes or no? You were also absent in the last class. Are you all right now? Got me? I don't know how many of you did this right. You did this right? Did you deploy the superimposition that I taught in the last class? See, it's such a easy tool to use, right? It comes in so handy, right? But I hope at least all of you have understood whatever I did, and you can connect it with the raft problem that we discussed for almost an hour, right? There are two bodies, m1 equal to 1 kg, m2 equal to 2 kgs, moving along the x-axis under the influence of mutual force only, Now, the velocity of their center of mass is 2 meters per second. That's given. All right. Now the x coordinate of m1. X coordinate of m1 for m1, this is for m1. The x coordinate of m1 with time in seconds, x in meters and time in seconds, is given as follows. We want to plot the x coordinate of m2 with time. This is the x coordinate of m1 with time. We want to be able to plot the x coordinate of m2 with time. Now also both masses are initially located at the origin. That means their center of mass is also located at the origin initially, right? Now t seconds later, at t equal to 0, what is the x coordinate of the center of mass? 0, right? Located at the origin. T seconds later, that means at an instant of time t, what is the x coordinate of the center of mass? 2 into t, because it's moving along the x-axis with a velocity of 2 meters per second. That means in t seconds it would have traversed 2t meters, yes or no? That's the x coordinate of the center of mass. T seconds later, yes or no? 2t, right? And that must be equal to m1 x1 plus m2 x2 by m1 plus m2, where x1 is the x coordinate of m1 at that instant, x2 is the x coordinate of m2 at that instant, yes or no? So m1 x1, that means 1 into x1 plus 2 into x2 by m1 plus m2, which is 3, yes or no? So this gives me like x2 equal to half of 6t minus x1. 6t minus x1, isn't it? 6t minus x1 by 2 is the x coordinate of m2. Now if x1 is known as a function of time, then x2 will be known as a function of time. Now there are two regimes. There are two regimes, t lying between 0 and 1 and t lying between 1 and 2, right? For each of these cases, the x coordinate of m2 would be separately evaluated, yes or no? So for t that lies between 0 and 1, this will give me x1 as a function of time. This will give me x1 as a function of time. And do you realize that this angle is 45 degrees? This angle is 45 degrees. So x1 as a function of time is x equal to t, isn't it? This is the line y equal to x kind of a thing. So x equal to t, this is x equal to t. The equation of this line is x equal to t, yes or no? x1 equal to t, yes or no? Tell me. No? Not sure about this? Now for t lying between 1 and 2, the equation of this line, this will be x1 as a function of time. And notice that this line is essentially, if you really think about it, this one 0. Now if this is 1 unit, this is 1 unit, then if you extend this, if this is 1 unit, this will also be 1 unit. That means this will be 2 units. This will be 2 units if I extrapolate this, yes or no? Do you see that? So that means the equation of this line would be x by 2 plus t by 2 equal to 1 would be the equation of the x by a plus y by b equal to 1. Yes or no? That would be the equation of this line. This could be looked upon as the x-intercept of this line. This could be looked upon as the y-intercept of this line. Yes or no? So x by 2 plus y by 2 equal to 1. That means x by 2 plus t by 2 equal to 1 would be the equation of this line. Chirayu. Right? That means the equation of this line is x plus t equal to 2. Instead of x, you have x1. Instead of x, you have x1. So then the equation of this line is x1 equal to 2 minus t for t lying between 1 and 2. Yes or no? So now I can find x2 as a function of time, x2 in this regime and x2 in this regime by suitably plugging in the values of x1 as functions of time. Is that okay so far? Look, for t lying between 0 and 1, this regime, x2 can be looked upon as half of 60 minus x1. x1 in this regime is t, which is essentially 5t by 2, which is 5t by 2, right? Now for t lying between 1 and 2, x2 can be looked upon as half of 60 minus x1. x1 is 2 minus t in this case. Which is half of 70 minus 2, which is 70 by 2 minus 1. Yes or no? That's x2 as a function of time in this regime. This is x2 as a function of time in this regime. Let me plot x2 versus time for both the regimes. Let me draw the graph. x2 versus t is also a straight line, as you can see, right? So let me draw the graph of x2 as a function of time. x2 in meters and t in seconds, right? For t between 0 and 1, x2 versus t is a straight line passing through the origin having a slope 5 by 2. At t equal to 1, x2 becomes 5 by 2. This tan of this is the slope, which is 5 by 2, right? Now, from 1 onwards, for t lying between 1 to 2, the slope has increased 70 by 2. 7 by 2 becomes the slope. It becomes a steeper graph, right? So from between 1 and 2, the graph becomes more vertical. It is steep. At t equal to 2, it will become 6. Yes or no? At t equal to 2, it will become 6 units. And the slope of this line is going to be 7 by 2 units. That means tan of this angle is going to be 7 by 2 units. Yes or no? This is the graph of x2 versus t. x2 versus t. Again, nothing difficult about it, really. All right. There is a particle of mass m moving in this direction. There is a particle of mass m moving in this direction with a velocity nv. Particle of mass m here moving along this line with a velocity nv. Right? And there is a particle of mass nm moving in this direction with a velocity v. moving in this direction with a velocity v. It is found that the center of mass of these particles moves along the angle bisector. This is theta by 2. This is also theta by 2. The center of mass moves like this along the angle bisector. This is m1, m2, this is the center of mass of the two particles, and it's found to move along the angle bisector between these two lines, right? We want to find the magnitude of VCM. We want to be able to find the magnitude of VCM. Clear? Okay. Now what I do is, say this is my x direction, this direction I choose as my x direction. Alright. This I select as my y direction. This angle is theta. Right? Both particles start from the origin. In t seconds, this would have moved a distance nvt here. This would have moved a distance nvt here. That means this length, first particle would have moved like nvt here. Right? And this, its x coordinate then would have become nvt cos theta and nvt sin theta. Would be the x and y coordinates of this particle. Yes or no? That means if r1 was the position vector of this particle, then r1 would be nvt cos theta I cap and nvt sin theta j cap would be the position vector of this particle. Yes or no? X I cap plus y j cap. So the position vector of particle 1 would have been nvt cos theta at an instant of time t plus nvt sin theta j cap. Yes or no? Whereas in t seconds, the other particle moving along the x-axis would have traversed a distance vt, right? The position vector of this particle then would be vt I cap. Position vector of this particle moving in this direction would have been in t seconds t I cap, right? Position vector would have been vt I cap. So far so good, right? Now, all's good, right? The center of mass lies, so this is position vector r1, this is position vector r2, and this would be position vector of the center of mass. This would be position vector of the center of mass, RCM, right? This is R1, this is R2, and this vector would be RCM. This vector would be RCM. Now, realize that if this is position vector R1, this is position vector R2, and this would be the angle bisector. An angle bisector, see if this is a triangle, say OAB. An angle bisector, internal angle bisector, divides the opposite side in the ratio of the sides containing the angle. You know that? This length OA is NVT. Do you realize that this length OA is NVT? This length is NVT. Whereas this length is VT. Yes or no? In t seconds, this length is Vt, position of this particle, and this is Nvt, right? And therefore, this length, by this length, say, let me call it C. AC by BC is going to be Nvt by Nm. Nvt by Vt, N is to 1, N is to 1. That means AC is to BC is going to be N is to 1. Yes or no? An internal angle bisector divides the opposite side in the ratio of the sides containing the angle. That means AC divided by BC is going to be NVT by VT, which is N is to 1. You've known of this property or not, right? That means this is going to be N is to 1, right? The position vector of A is R1, position vector of B is R2. Now this is the center of mass. It has position vector RCM. It has position vector RCM. Then from section formula, which applies to position vectors as well, section formula applies to position vector as well, RCM. The position vector of the center of mass from section formula is going to be N into R2 plus 1 into R1 by N plus N is going to be the position vector of the center of mass from section formula. So 1 into R1 plus N into R2 by N plus 1. That's going to be the position vector of the center of mass, yes or no? Clear? Let me see what transpires. RCM then is R1, which is this, NVT cos theta I cap plus NVT sin theta j cap plus NVT I cap. N times R2, right? Divided by N plus 1, yes or no? Does it sound all right? All's good? Which then reduces to Vt if I took common by N plus 1 N cos theta NVT I can take common actually, so that will be 1 plus cos theta I cap plus sin theta j cap, just collecting terms, NVT, right? See, this I cap terms taken common, and this, and then I take NVT common. This is what turns out to be the position vector of the center of mass. If I differentiate this, what would I get? Velocity of the center of mass, right? So on differentiating this, velocity of the center of mass then becomes NV by N plus 1 into 1 plus cos theta I cap plus sin theta j cap. That becomes the velocity of the center of mass. I need to find the magnitude of this vector. Mod VCM is the magnitude of this vector. Magnitude of the velocity of the center of mass then will become NV by N plus 1, magnitude of this vector, which is 1 plus cos theta whole squared plus sin square theta. That's the magnitude of this vector, yes or no? Which is NV by N plus 1. Cos square theta plus sin square theta 1. 1 plus 1, 2. 2 plus 2 cos theta is what this would become. 2 plus 2 cos theta. So root 2 into 1 plus cos theta. And 1 plus cos theta you can write as 2 cos square theta by 2. 1 plus cos theta you can write as 2 cos square theta by 2, yes or no? So this is like NV by N plus 1, 2 cos theta by 2. 1 plus cos theta is 2 cos square theta by 2, yes or no? Again a simple problem, just to be represented suitably, that's all. How many of you got this right? Okay. Your answer matches? Which is the same thing. I mean, I just use I cap, J cap for those components. It's, in principle, deep down, it's the same thing, but just about a representation. Your answer matches? So there is a 30, 60, 90 inclined plane. This is 90 then. There is mass m here. There is mass m here. The inclined plane is fixed. We want to find the magnitude of the acceleration of the center of mass of the two blocks. Now, if this is fixed, then the acceleration of this in this direction is going to be g sine 30 degrees. Yes or no? Right? The acceleration of this is going to be g sine 60 degrees. Now what you can do is, since these two lines are perpendicular to each other, we can call them the x and the y directions respectively, right? So the acceleration of the center of mass is going to be m1 a1 m into g sine 30 degrees I cap plus m into g sine 60 degrees j cap divided by m1 plus m2, which is 2m. That's the acceleration of the center of mass, right? So which is like g by 2 I cap by 2 plus root 3 j cap by 2. That's the acceleration of the center of mass vector. Yes, Ayush, please ask me questions. So magnitude of the acceleration of the center of mass is going to be g by 2 into root half squared plus root 3 by 2 squared, which is g by 2. Yes or no? That's the acceleration of the center of mass. No? Clear? Okay, very straight, direct application, so I was hoping that you'll be able to get it right yourself, right? Number 7. Two bodies of the same mass lie together, m and m, right? And they're tied by a string. They're tied by a string. The string that ties them, initially the string is collapsed. So you're not able to see the string. All right. Now one of them is projected upwards with a velocity root 6gl. So while this one is projected with a velocity root 6gl, the upper one, say, the string between them, which is initially collapsed, begins to straighten up, but as long as the string is not taut once again, the second mass will not feel any force, right? After a while, what happens is, this mass, the lower mass, remains on the ground, whereas the upper mass, which was initially fired with a velocity root 6gl, reaches this position and its velocity becomes, say, v1. And now the string length becomes, the string becomes taut. Now once it becomes taut, because of this velocity, this will start to move up. Because there is impulse in the string. There is impulse because of the tension that builds up in the string, yes or no? And that impulse of the tension will build velocity in this mass, and this will move up. The center of mass of the system moves up now, right? Okay. Now at this point, the velocity of this is 0. And this mass only under the influence of gravity, because while it was moving up to this position, the string did not have any influence because the string remained collapsed. So it moved up solely under the influence of gravity, and by the time it traversed a distance L units, it acquired a velocity v1 meters per second, and very clearly v1 squared is the initial velocity v squared minus 2g into the upward distance covered. Yes or no? Got me, no? v1 squared is 6gl, so this will become 4gl. v1 then would be 2 root gl at this instant. Right? The velocity of the center of mass at such an instant. This is 0 velocity. This is velocity v1 at this instant. Length L. Forget this. Center of mass then would have a velocity m v1 plus m into 0 by m plus n. That will be the velocity of the center of mass. Yes or no? M into v1 plus m into 0 by 2m. That's going to be the velocity of the center of mass. The velocity of the center of mass will then be mv1 plus 0 into m divided by 2m. That makes it v1 by 2. v1 by 2 is the velocity of the center of mass at this instant, right? vcm. Now, from this point, the center of mass moves under the influence of gravity. The center of mass moves under the influence of gravity. With an initial velocity vcm, let's say initially the center of mass is at a height L by 2 from the bottom, and it has an initial velocity vcm, right? From this point, under the influence of gravity, g acting downwards, the center of mass will acquire a maximum height. The center of mass will acquire a maximum height, h max, from this position. H max is going to be what? vcm squared by 2g? No? vcm squared by 2g, the maximum height acquired by the center of mass. So h max from this position is vcm squared by 2g. Huh? Which part? Tell me. The center of mass has a velocity vcm at this point, which we have computed, m1 v1 plus m2 v2 by m1 plus m2, which is v1 by 2, right? Now, center of mass is acted upon by gravity downwards. So the maximum height reached is going to be u squared by 2g, isn't it? U is vcm. Maximum height under the influence of gravity is u squared by 2g. So vcm squared by 2g, isn't it? vcm squared by 2g. vcm, as you can see, is v1 by 2, which means root gl. So gl by 2g, which is L by 2. That means from this point onwards, it acquires a maximum height L by 2, plus it is already at a height L by 2. That means the maximum height from the ground is going to be L by 2 plus L by 2. That makes it L units from the ground is the maximum height from the ground acquired by the center of mass in the process. The center of mass is the combined effect of all masses put together. While computing this mv1 plus mv2 by m1 plus m2, I have built into the velocity of the center of mass the impact of both the masses. That's the whole idea behind the center of mass concept, isn't it? And then center of mass will have to be looked upon from the purview of only external forces acting on the system. I mean, you might be tempted to believe that, hey, why is the tension not producing any impact on the center of mass? No, because that's internal. To a system comprising the upper mass and the lower mass, tension becomes an internal force and will have no consequence on the motion of the center of mass. The only conceivable external force acting on the system comprising the two masses is gravity alone, which the center of mass will report and will act commensurate. This is how it goes. Which is then VCM squared by 2g, etc. Regulation affair. Clear? Are you all okay with this or not? Number 8, there is a smooth fixed pulley. Smooth fixed pulley. There is a platform here. This platform has mass small m, and the man on the platform has mass capital M. That means this system has mass small m plus capital M. Alright. And is balanced by a counterweight here, which is capital M plus small m. Capital M plus small m. Okay. Now this man, monkey incarnate, jumps up with a velocity u, itching to jump, jumps up with a velocity u. This man jumps up with a velocity u. We want to find the distance through which this platform will descend. We want to be able to find the distance through which this platform will descend. All right. All of you understood the concept of impulse in the last class, right? All of you understood the concept of impulse. Now, when this fella wants to jump, he ought to exert a force on the platform downwards for a small time. That means he exerts on the platform a downward impulse. He exerts on the platform a downward impulse, yes or no? The platform in turn exerts on him an upward impulse, which causes the change in linear momentum of the mass. This is what transpires. You know what I'm saying? So when the man exerts on the platform a downward impulse J1, the platform exerts on the man an upward impulse J1. Impulses will obey Newton's third law. Right? They would be equal in magnitude and oppositely directed. What would this J1 do to this man? It will change the linear momentum of the man by mu. Right? So what has this J1 done to the man? It has brought about capital M into u on the man. Change in linear momentum in the upward direction. Yes or no? Okay. Now, look at the platform side of the story. This is the man's side of the story. Done. Look at the platform side of the story. The moment the platform experiences a downward impulse from the man, there would be an additional tension built up in the string. There would be an impulsive string force that will develop. So the platform now, imagine, will experience, because of the string will now exert an upward impulsive force on the platform. Say the impulse because of the string is J2 on the platform, isn't it? It's going to be upwards only, isn't it? The string will always pull, will never push. The string will, so the impulse because of the string on the platform is going to be J2 upwards, yes or no? Now, as a consequence of these two impulses, the platform, which is now of mass small m, develops a velocity v downwards. Yes or no? The platform, because of the difference in these two impulses, will develop a velocity v downwards. So can I not say from the platform side of the story, net downward impulse, which is J1 minus J2, is change in linear momentum of the platform in the downward direction, which is m into v? Yes or no? Now, look at this mass. Now, the impulse in the tension will be same everywhere, right? So, this balancing weight will experience impulse because of the string in the upward direction, J2, Yes or no? And would you mind believing that if the platform develops a downward velocity v, this balancing weight will also develop a velocity v upwards? String constraint, yeah, that's ordinary string constraint. So can I not say that this J2 must be capital M plus small m into v? My objective is first to find the velocity of the platform right after the man leaps up. V is the velocity of the platform downwards and of this mass upwards right after the man leaps up with a velocity u. In this, plug in J1 equal to capital M into u. In equation 2, capital M into u minus J2, which is capital M plus small m into v. That must be small m into v. Yes or no? U is known to me and v is obtained from this. V then, the velocity right after the man jumps turns out to be capital mu divided by capital M plus 2m. Yes or no? That's the velocity of the platform downwards and of this balancing weight upwards right after the man leaps. Yes or no? Do you understand this? Now. So now the man is in midair. The man is in midair. The platform is descending down. But realize that the mass here is more than the mass here. So even though the velocity of this platform is downwards, the acceleration of the system of capital M plus m is going to be downwards, and of the platform the acceleration will be upwards. Okay. See bhai, will the acceleration ever depend on the velocity? This mass is small m, this mass here is capital M plus small m. If you have to find the acceleration of the system, will it depend on the velocity of the system? Of course not. It will depend on the forces, isn't it? Now this mass is more than this mass. So the even though this mass has an upward velocity and this has a downward velocity, since this mass is more than this mass, the acceleration of this mass is going to be a downwards, acceleration of this mass is going to be a upwards. Yes or no? If I had not given you the velocities of the two masses, what would happen? Capital M plus small m would move down and small m will move up. Right? The acceleration of this would be downwards, the acceleration of this would be upwards. And how did we compute the acceleration of these two? Capital M plus small m into g minus small m into g divided by m1 plus m2. That's how we computed the accelerations, right? Which means this will retard, this will also retard. It has a downward velocity but upward acceleration, so this will retard. It's going to move down with an initial velocity v downwards but upward acceleration, so the velocity of small m will eventually become 0 somewhere under the influence of this retardation a, right? So what is this a? This a, as has been computed time and again, this a is capital M plus small m into g minus small m into g divided by the sum of the masses, which is capital Mg divided by capital M plus 2m. Yes or no? So now this mass has a velocity v downwards, which we have computed, and has an acceleration a upwards. That means it's retarding, right? At some point, the velocity of this will become 0, and by the time its velocity, so this mass of small m has an upward acceleration a, has a velocity v downwards, and at some instant its velocity will become 0 because it's being retarded. By then it would have traversed a distance d. The platform would have traversed a distance d by then. So can I not say v squared, 0 squared minus v squared is minus 2a into d? That means v squared is 2ad. V squared is 2ad, yes or no? So v squared for the platform is 2 times A into D. Bolo, ask me. Sure, na? 0 squared minus V squared is minus 2A into D. I have taken downward positive, upward negative. Right? So minus minus will get cancelled. So 2A into D. So V is known to me. We have computed V earlier, right? A is known to me, which is this. So the distance, downward descent of the platform D can be obtained from V squared by 2A is the downward descent of the platform. Yes or no? Now I have another remark here. So from this point onwards, once the velocity of the platform becomes 0, it will move up with an acceleration A, right? And the man, he leaps up. He's not leaping up with a velocity greater than the escape velocity for Earth, right? He will also descend. He will reach a highest point and will descend. The platform, after having gone to its bottommost point, will ascend. They will once again meet. I claim that they meet at the same point where the man leapt from the platform. Check that out. I claim, and I mean it, and for you to establish that the man eventually will descend, the platform will ascend, and therefore the man would once again fall on the platform until and unless, you know, he does acrobatics in air and does weird things and a rocket comes and hits him and, you know, he goes into a different orbit. But under ideal conditions, the man would once again fall on the platform and at the same position where he leapt up from the platform. Check that yourself, right? But are you all okay with whatever I've communicated so far on this, right? Number 9. Hey, center of mass of a body, option A, lies at the geometrical center. Rubbish. Not necessarily. Always lies inside the body? No, not necessarily. Lies outside the body? No. It could lie anywhere. It could lie anywhere, right? So, option D, 9D. 10. A system comprises of two particles, small m and capital M, where capital M is larger than small m. Capital M is larger than small m. The center of mass will always be closer to the heavier body. So the center of mass will be here and it will always be closer to the heavier body, right? Again, you know, these must be very ordinary outcomes. Now, all particles of a body are situated at a distance r from the origin. If this is the origin, then on a sphere of radius r, there are very many particles, say mass m1, mass m2, mass m3, mass mn located. This is the origin. The distance of the center of mass of the body from the origin. This system has a certain center of mass. Its distance from the origin would be what? Less than r, greater than r, or can't say anything, equal to r. Yes. So just to take stock of things, position vector of m1 is r1, position vector of m2 is r2, and so on and so forth. mn is rn. So the position vector of the system, just to give you a formal take on this, position vector of the center of mass is going to be what? m1 r1 plus m2 r2 plus mn rn divided by m1 plus m2 plus mn. Yes or no? By definition, right now. Now what I need is this is the position vector of the center of mass, wherever it be. If this is O and if this is the center of mass, then this is the position vector of the center of mass. What I need is its distance from the origin. That means I need the value of magnitude of the center of mass, magnitude of the position vector of the center of mass. This length is mod of RCM, yes or no? And realize that even though these vectors R1, R2, R3, Rn are different, but mod R1 will be the radius R, mod R2 will be the radius R, mod Rn will be the radius R, yes or no? That means mod R1 is the same as mod R2 is the same as mod Rn. Each will be equal to R, yes or no? I need mod RCM. I need mod RCM. Now mod RCM will be mod of this. Will be mod of this. Hey, but mod of A1 plus A2 plus AN, triangle inequality, is less than or equal to, modulus of the sum will always be less than or equal to sum of the moduli. Yes or no? Modulus of the sum will be always less than or equal to sum of the moduli, right? So modulus of the sum will always be less than or equal to sum of the moduli, M1 mod R1 plus M2 mod R2 plus Mn mod Rn by M1 plus M2 plus Mn. Yes or no? Hey, but mod R1, mod R2, mod Rn, each will be equal to the radius R, right? So this will be less than or equal to mod R1, mod R2, mod Rn, each replaced by R. Then inside you have M1 plus M2 plus Mn by M1 plus M2 plus Mn, which is 1. So will be less than or equal to R. Just a formal way of looking at things. Intuitively, it is so obvious. Intuitively, it is very obvious, but just a formal take on things. Got me? And you know, just a quick one on, you know, why I deployed this triangle inequality, and just to geometrically assess this. See, if I had a vector A1 and a vector A2, all right, then the diagonal of this parallelogram will be the vector A1 plus A2, isn't it? That's the vector representation of the diagonal. Now, this length is going to be mod of A1 plus A2. This length is going to be mod of A1, and this length, which is the same as this length, is going to be mod of A2. Then triangle inequality means the third side of the triangle, which is of length mod of A1 plus A2, cannot exceed sum of the other two sides. This is mod A1, this is mod A2. That's a triangle inequality. Ayush. And this can be extended. Suppose I had three vectors, A1 plus A2 plus A3. Then look at how we can handle things inductively. Let's look at this as A and this as B. So mod of A plus B will be less than or equal to mod of A plus mod of B. Yes or no? Isn't it? But mod A1 plus A2 will be less than or equal to mod A1 plus mod A2, right? So this is less than or equal to mod A1 plus mod A2 plus mod A3. And this can be extended to any number of vectors. This can be extended to any number of vectors. The triangle inequality, right? Clear now? So 11 less than or equal to capital R, which is option Bombay. Option Bombay. Three rods. One say a rod OA. A is A0 this must be A0. say OB, P must be 0A, and this is a third rod. This is one rod OA, OB and AB. I want to be able to find the center of mass of the system. Center of mass of the system. Okay. As far as OA is concerned, what's the center of mass of this? A by 2, 0. For this mass, this is mass M, right? As far as this is concerned, what's the center of mass of this? 0, comma A by 2. The center of mass of this is going to be A by 2, comma A by 2, halfway between these two, which is A by 2, comma A by 2. So the center of mass of this is going to be A by 2, comma A by 2. Yes or no? So now, the x coordinate of the center of mass of the system is going to be mass into x coordinate of the center of mass of this, which is A by 2, plus mass into x coordinate of the center of mass of this, which is 0, plus m into x coordinate of the center of mass of this, which is A by 2, divided by 3m, total mass 3m, yes or no? Which is A by 3. And similarly, the y coordinate of the center of mass m1 y1 plus m2 y2 will also turn out to be A by 3 of the system. Got me? Clear? Number 13. There is a mass capital M here, and there is a rope here, say. The mass of this rope is M minus small m. Capital M minus small m is the mass of this rope. Then there is a person of mass small m. There is a person of mass small m trying to climb up the ladder, and its displacement with respect to the ladder, small m, and this is the ladder, not the rope, okay. Its displacement with respect to the ladder is found to be delta r, say, upwards, is found to be delta r. Displacement with respect to the ladder is found to be delta r upwards. We want to be able to find the displacement of the center of mass of the system. System means this mass, the ladder, and this mass. If this small m, with respect, not with respect to the ground, but with respect to the ladder, has an upward displacement delta r, what then with respect to the ground would be the displacement of the center of mass of the system? That is sought here. Okay, just to look at things in an organized manner here too. Okay, let me look at the various entities here. Say, measured with respect to the ground, the position vector of this is r1, say, at any given instant. For the ladder, which can be replaced by a point particle at its midpoint, the center of mass, let's say r2, right? And with respect to the ladder, let's say this mass with respect to the ladder is r. With respect to the ladder, with respect to the center of mass of the ladder, let's say this mass is located by r. That means with respect to the ground, this mass is going to be r2 plus r. Yes or no? We have set up ground for the positions of various entities here. Now, the center of mass of the system then is going to be capital M into r1 plus capital minus m minus small m into r2 right, plus small m into r2 plus r, where r is the position of the man with respect to the ladder, but r2 plus r is the absolute position of the man. divided by the total mass of the system, which is 2m. Yes or no? Very clearly, small m into R2 would get cancelled with small m into R2 here, leaving you with capital M into R1 plus capital M into R2 plus small m into R divided by 2m. Yes or no? Okay, now, very simple. This mass and this ladder would get displaced by equal amounts but in opposite directions. Yes or no? This mass capital M and the ladder would get displaced by equal amounts but in opposite directions. Right? That means vectorially speaking, change in position of this is change in R1. Vector R1. Change in position of the ladder is change in position vector of R2. And these two vectors must be equal in magnitude but opposite in direction. The ladder plus this mass m would move in opposite directions but by equal amounts because of a string consideration. Can I not say this? Now what is it that I want to find? R is the position of m with respect to the ladder, and R changes by an amount, delta R. R changes by an amount, delta R. I want to find delta RCM. I want to find delta RCM, change in the position of the center of mass. Yes or no? So change in the position of the center of mass is going to be capital M into change in R1 plus capital M into change in R2 plus small m into change in R divided by 2m. Yes or no? But delta R1 is minus delta R2. So these two numbers would cancel off, leaving you with m into delta R divided by 2m. That's a change in the position of the center of mass of the system. Yes or no? Are you all comfortable with this? Make sense now? In problem 14, there is a hemisphere of radius small r. There is a hemisphere of radius small r and of mass 4m. The mass of the hemisphere is 4m. Radius capital R, say. And it lies on a smooth horizontal surface. The hemisphere lies on a smooth horizontal surface. A particle of mass small m is placed on top of the hemisphere. Find the angular velocity of the particle with respect to the hemisphere at an angular displacement theta when the velocity of the hemisphere becomes v. Hey, when this falls down, why would the hemisphere move leftwards? Let's say when this mass falls down, why would the hemisphere move leftwards? Yes, to x coordinate of the center of mass should remain preserved, right? Or what you can say is the total horizontal linear momentum of the system is 0. When this moves like this mass develops a rightward velocity. To compensate and to maintain 0 horizontal velocity, the hemisphere moves to the left to maintain 0 horizontal linear momentum. Why 0 horizontal linear momentum? Because on a system comprising the particle plus the hemisphere, there are no horizontal forces acting on the system externally. So the horizontal linear momentum, which is initially 0, will remain 0 at all times, right? Okay. So after a while, when the particle moves to this position, Now one thing, if the particle is not losing contact with the hemisphere, see, why would a particle lose contact with the hemisphere? The moment, see, there is a tangential direction, and there is a normal direction, which is the radial direction, right? Loss of contact is whatever happens in this direction. If the particle has a non-zero component of velocity with respect to the hemisphere in this direction, then it will lose contact. Right? But with respect to the hemisphere, if it has no velocity in this direction, relative to the hemisphere, it will maintain contact. That means the relative velocity of the particle in this direction with respect to the hemisphere must be 0. That means the net velocity of the particle with respect to the hemisphere will be simply in this direction, vrel. The relative velocity of the particle with respect to the hemisphere will be always along the tangent to the hemisphere, so that the particle does not lose contact with the hemisphere. If any component of the relative velocity is in the normal direction, then that will cause the hemisphere to part with the particle. Partition happens because there is relative motion in this direction, will cause partition, right? Otherwise, they would maintain contact. Yes or no? Are you all okay with this idea? Okay. So one thing for sure, the relative velocity of the particle will be vrel like this. With respect to the hemisphere would be along the tangent. Now, the hemisphere at this instant has developed a velocity v as seen by a ground observer. Now, what is the absolute velocity of the mass m? Horizontally, suppose this angle is theta. Do you realize that this angle will also be theta? Because if this makes an angle theta with the vertical, right, a perpendicular to this will make an angle theta with the horizontal. That's how you should look at it. If a certain line makes an angle theta with the vertical, then a line perpendicular to that line will make the same angle with the horizontal. So this angle must be theta. Now, so vrel could have been resolved as vrel cos theta horizontally and vrel sin theta vertically. I don't care about the vertical component, right? Which means in the horizontal direction, what's the velocity of m in the horizontal direction? Relative velocity plus the velocity of the observer. Relative velocity in the horizontal direction is vrel cos theta, and the velocity of the observer in the horizontal direction is minus v. So minus v, that's the absolute velocity of the mass m horizontally at this instant. The velocity of the hemisphere is v like this, and the algebraic sum of the linear momentum of the hemisphere plus the particle must be 0 in the horizontal direction. That means the linear momentum of the particle in this direction must be equal to linear momentum of the hemisphere in this direction, so that the algebraic sum of their linear momenta in the horizontal direction remains 0, right? So which means this m into this vrel cos theta minus v is the velocity of the hemisphere horizontally, of the particle horizontally, vrel cos theta minus v. Pradyum, got me? Nahi? M into vrel cos theta minus v, which is the absolute velocity of the particle rightwards, and that must be equal to the linear momentum of the hemisphere leftwards, which is 4mv. Yes or no? Minus v, vrel cos theta minus v. Sorry. So this gives me vrel equal to 5v by cos theta. Yes or no? Now what is it that I mean by this relative velocity? It's as if the hemisphere is at rest and this particle has a velocity tangential like this. This angle is theta, as if the hemisphere is at rest. That means the angular velocity is going to be the tangential velocity vrel divided by the radius r would be the angular velocity with respect to the hemisphere, vrel by r, right? So vrel by r, which is omega, then would be vrel by r, which is 5v cos theta, 5v by r cos theta. Clear? Let's look at the next situation. So all that we did was we conserved linear momentum of the particle plus hemisphere in the horizontal direction. Why? Because there were no horizontal forces acting on the system horizontally. In the vertical direction, I couldn't have preserved linear momentum because there was unbalanced gravity acting on the system, right? Mother Earth, as you pointed out. There is an impulse. This is a string. This is a string, right? And on this mass, there is an impulse J1, which is 10 Newton second acting. This is an inextensible massless spring, and this is 30 degrees, so this will also be 30 degrees. Assuming that the string remains taut after the impulse, what is the magnitude of the impulse of tension? What's the magnitude of the impulse of tension? Because right after this impulse is applied, the tension in the string will get invoked. The tension in the string will get invoked. Look, there would be tension in the string. And there would be impulse of, and the impulse of the tension will act along the string. Yes or no? JT, say, impulse of the tension. Right? And what would this impulse do to this mass? It will develop on this mass a velocity in this direction. So on this direction, a velocity v would develop on this mass. So can I not say that impulse of the tension when applied on this mass, JT, must be mass of this into velocity v? So 1 into v? Yes or no? Okay. Now the important thing is, if this mass develops a velocity v like this, then along the string, both masses must have the same velocity so that the string remains taut. That means in this direction, along this direction, the component of the velocity of this mass in this direction must also be v. In addition, it will also have a velocity like this, but along the string, the component of their velocities along the string must be the same in order that the string could remain taut. In order that the string could remain taut. Yes or no? Now, what are the impulses acting on this mass? There is J1 acting like this, and then there is impulse because of the tension in the string, which is JT like this acting on this mass. Yes or no? On this mass also there is string force acting for a short time, right? The net impulse in this direction on this mass is what? J1 cos 30 degrees. Net impulse in this direction, J1 cos 30 degrees minus JT is change in linear momentum in this direction, which is 1 into V, right? Yes or no? 1 into V is JT. So this is JT, as you can see, right? So 2JT is J1 cos 30 degrees. J1 cos 30 degrees means 10 into root 3 by 2, which is 5 root 3. So impulse of the tension is 5 root 3 by 2 Newton second. Yes or no? Got me? And then the last problem of the sheet. There is a square lamina like this. There is a square lamina like this, and this is a square of side A units. A units. And from this square, a semicircular lamina is cut off. A semicircular lamina is cut off. And the center of this is referred to as the origin, right? This is the x-axis and this is the y-axis. Very clearly, this length is going to be a by 2, right? Now, what is done is, with this as the diameter, that means of radius a by 2, a semicircular strip is cut off. A semicircular strip is cut off. This is x, this is O, this is y. This is cut off, leaving you with this. Right? This portion is cut off from this, leaving you with this. For this portion, I want to be able to find the center of mass. Again, you know, for a uniform mass distribution, this law of symmetry will hold good. The center of mass will still lie along the x-axis. Now, in the earlier case, it was at O, the geometrical center of the square, because the region to the left and the region to the right were of equal masses. But now, the center of mass will shift leftwards along the x-axis, because now the left side has become heavier, So the x-coordinate of the center of mass of the system would be negative now. It should turn out to be negative. Now, remember, the center of mass of this lies of a semicircular strip is at a distance 4r by 3 pi. Was this discussed? 4r by 3 pi in this direction. Okay. Now, what is the mass of this whole thing? M. Mass per unit area is a squared. Mass per unit area is a squared. So, what's the mass of this into the area of this? This radius is a by 2. So, the mass of the semicircular strip is mass per unit area into the area of this region. Area of this region is pi a squared by 4 by 2. Pi a squared by 4 by 2, which is m pi by 8. M pi by 8, yes or no? That's the mass of the semicircular region. Now, did I tell you that the x coordinate of the center of mass of this would be mass of this into x coordinate of the center of mass of the uncut portion? So, x coordinate of the center of mass of the remaining is going to be what? Mass of the uncut region, which is m, into the x coordinate of the center of the uncut region, which is 0, minus the mass of the region which is cut, which is m pi by 8, into the x coordinate of this, which is r minus 4r by 3 pi. X coordinate of this is r minus 4r by 3 pi. This is r minus 4r by 3 pi. Divided by m1 minus m2. That means m minus m pi by 8. Yes or no? And very clearly it turns out to be a negative number. That means it has shifted leftwards. This would be the x coordinate of the center of y coordinate of the center of mass of the system is going to be 0, because the region above the x-axis and below the x-axis look identical anyways.